This conference will now be recorded.
All right. Take it away.
Right, Colin, whenever you're ready.
Colin, we can't hear you.
Did something happen to Colin?
Can you hear me?
I can hear you, yeah.
Huh. Colin, maybe you could try calling in.
I switched to another group, but I'm afraid we might not get Camilla's screen back again. Okay, so Colin phone.
Hello.
Hello? Is that Colin?
Yeah, can you hear me now?
Yes. Excellent. Yeah. Okay. Take it away.
All right, we'll do it this way.
Progressive.
Okay, how is audio quality? Sufficient?
Good.
Great.
Okay. Did everybody else figure out their audio? I see a lot of things in the chat that say audio is not working. No. Okay. Katrina, Camilla, are we good to go?
Yeah.
Yep, we're good.
Okay. Cool. Alrighty. Hi everyone. My name is Colin Rowland. I'll be presenting with Camilla Abe and Katrina Rabler on soil thermal conductivity parameterizations in the SUMO modeling framework. Just an FYI, we're all from UW-Madison, and we're getting our first snow today. Next slide. Cool. So SUMA offers 3 schemes for computing soil thermal conductivity. I'll refer to those as function soil wet, mixed constituent, and Hansen VZJ. And so sort of our project, we're exploring the effects of these different parameterizations for soil thermal conductivity on a variety of hydrological parameters, as well as sort of state variables in the soil snow domain. Next slide. So what is soil thermal conductivity? You've probably heard of hydraulic conductivity for porous media. Thermal conductivity is the analogous parameter that describes the flow of heat rather than the flow of a fluid through a porous media. And so that's going to vary with a couple of things, including mineralogy. You might think the amount of quartz or the amount of clay in a soil is going to control sort of how heat moves through it, as well as its porosity and the saturation of that porosity with respect to liquid, frozen, and gaseous phases. So SUMA calculates a bulk thermal conductivity for the soil domain for each layer, whatever your layering schema might be, and it just sort of amalgamates the different phases, right? The soil, the liquid, and the gas phases. And all of that goes into the right side of equation 3, which is shown here on the slide. It goes into the flux term, right? How quickly can heat move through the soil domain is going to be a function of that soil thermal conductivity. And I have these series models and parallel models down here at the bottom of the slide, just to note that SUMA is not explicitly modeling the individual phases, rather it's calculating a bulk sort of summation of thermal conductivity, rather than trying to figure out how heat flows through the gas phase, through the liquid phase, through the solid phase. Next slide. All right, so here's a lot of math. Our forcing files that we're using for our model are the Umpqua 1996 to 97 forcing files, and our model structure is a 5-layer CLM snow layering. We also have 5 layers in our soil domain. So what are these 3 parameterizations? We have mixed constituents, which is, as you can see, just sort of the sum of the fraction of the domain, that theta term, that is air, liquid, ice, or soil, times the thermal conductivity of that particular component, and it just sums the individual components. And here on this slide, the gammas and the kappas mean the same thing. They're both soil thermal conductivity. Function soil wet, on the other hand, sort of scales everything by this K sub E term called the Kernsten number. It's just a different way for calculating soil thermal conductivity. And then Hansen VZJ is a lot more complicated. It tries to include sort of dispersivity of heat within the domain coupled with flow processes. And so it gets sort of nasty, and it has a bunch of constants and functions in it. Those are sort of experimentally derived from column experiments with freezing and unfreezing of soil columns. Next slide. All right, so what are the results? So here's the soil thermal conductivity that SUMA computed using these 3 different parameterizations. And the big thing to note is that mixed constituent soil thermal conductivity is greater than the function soil wet soil thermal conductivity, which is also greater than the Hansen VZJ soil thermal conductivity. And not huge differences, but 3.5 to 2 to 1 watts per meter per Kelvin. Hopefully we'll see that has some interesting results for some other things that we're interested in. And I'll hand it off to Camilla.
Hi. So now let's look at the effects of thermal conductivity on soil ice content and snow water equivalent. Overall, in the ice content, we can see that we can see a small peak between January and February of '97, which coincides with the lowest snow surface temperature of the series here. We hypothesized that between January and February, the snowpack was not sufficient to insulate the soil to prevent soil water to freeze. We can also see that snow ice increases from March to April, which is in the spring. And we hypothesized that this is because the snow starts to melt and the soil water starts to freeze because it loses the insulation provided by the snow. Now comparing the different simulations, we can see that mixed constituent resulted in more ice content, followed by soil wet and Hansen simulations. We hypothesized that since mixed constituent has the highest thermal conductivity, the soil tends to lose more energy more quickly than in the other simulations, thus resulting in more and earlier ice formation. You can see in the graph of the middle here. The opposite occurs in Hansen simulation, and soil wet is an intermediate simulation. We can think of the same way to explain Swee plots here in the bottom, where mixed constituent resulted in less Swee than soil wet and Hansen simulations respectively. We understand that the high thermal conductivity in mixed constituents simulation allowed for heat to be transferred more easily from the soil to the snowpack, which reduced Swee. Again, the opposite happened with Hansen simulation, and soil wet was again an intermediate. We can also see here in the end of the series that the differences in thermal conductivity did not translate in snow melt timing, since snow melts in the same period for all simulations. Now looking at the soil temperature profile, we can see that simulation with mixed constituent here in the top presents the lowest temperatures for most of the time and for most of the soil layers. And this happens because the high thermal conductivity allows for relatively intense and quick heat transfer from the soil layers to the surface. On the other hand, mixed constituent was also the simulation that resulted in the highest temperature reaching deeper in the soil during the spring. And this is also because of the high thermal conductivity that also allows the heat from the surface to reach deeper in the soil. Again, we can see an opposite behavior for Hansen simulation and an intermediate behavior for soil wet simulation. Now I'll hand it to Katrina, who's going to talk about some effects on the hydrologic cycle.
Hi everyone. So yeah, I looked at infiltration, sublimation, and runoff, some of these big overall mass balance variables that we would look at in evaluating a model. So most of the differences occurred during the infiltration, or sorry, during the spring runoff and during the spring snow melt. But there weren't big differences in infiltration and runoff. There was, however, a pretty big difference in sublimation rates. So the Hansen simulation had the most sublimation, followed by soil wet, and then followed by mixed constituent. And so we also, up in the top right, calculated the percent difference of means. So these are all with respect to mixed constituent. And all of these numbers are with Hansen with respect to mixed constituent, since those have the greatest difference. And so there's a 31% difference in sublimation rates. And so we hypothesized that Hansen, since it has the lower soil conductivity, this led to warmer soil temperatures over the course of the winter, which would have led to more sublimation because there's more energy available for sublimation to occur. And similarly, soil wet had the lowest sublimation rates, which corresponded to its higher soil conductivity. Next slide, please. And so to conclude, the choice of soil thermal conductivity scheme has implications for energy, flux, and phase change processes. And as we explained, these changes in turn affected Swee, ice content, sublimation, and other parameters. And so if we had more time and had other data sets, we would have looked at this in places with different climates, different soil textures, over longer periods of time, and looking at climate change scenarios as well. So here's a little picture that I had of Oregon, a little ways away from Umpqua. And next slide, these are references. And next slide. And thank you. And here's a little shot of some snow from Madison, Wisconsin.
Thank you.
Awesome, thank you. Any questions for the presenters? Anybody? I'll start. I'm Katrina. When you were showing sublimation, were you showing snow sublimation or sublimation from the soil when there wasn't snow on it?
It was just snow sublimation.
So why do you think that the soil conductivity, which happens at the bottom of the snowpack, would make a difference in the snow sublimation at the top of the snowpack?
Yeah, we were a little perplexed by the big difference. You know, I guess higher soil, more heat in the soil would give more energy to the snowpack, make the snowpack warmer, and then there could be more sublimation. And then the reverse would be true in terms of condensation on the snow. So a colder snowpack or a colder soil layer would lead to a colder snowpack and then more condensation occurring on the snowpack. But we weren't really sure, you know, there are probably other variables that are affecting sublimation that we didn't have time to test.
Did you zoom in to, it looks like most of the difference is really here at the end in like April from your graphs you have up on the screen.
Yeah.
I'm wondering, did you zoom into like what the snow surface temperature said on like that week, or if the snow might have disappeared in one of them just like a day or two earlier?
Do we have more graphs of, I think we have surface temperature down below, right, Camila?
Yeah, we have surface temperature here.
Yeah, I can't tell.
Yeah, but we haven't zoomed in this period specifically.
I think we zoomed in in one of these graphs.
Here, you mean?
Snow surface temperature in the top right. Yep.
Yeah.
So there are bigger differences right around springtime.
So once it goes above 273, it's not snow anymore, right? It's soil.
Mm-hmm.
Oh, yeah.
So maybe that's sublimation from the soil.
I think so. I think you're switching to the soil, and it's not the snow anymore. Yeah.
Okay, even though the variable is called snow sublimation.
Well, yeah. Well, this one that you have labeled snow surface temperature is called surface temperature, and it changes to what it is. I think, yeah, I think we want to check exactly which sublimation variable it is, and if there's ice. I think you could be getting into something weird, like you remember I was showing you like snow without a layer, if there's ice in the soil.
Okay. Yeah, the variable I did use throughout was scalar snow sublimation.
So you think, yeah. You don't have to ask. It's worth checking because
Like checking.
Yeah, it doesn't make physical sense that it would, in the real world make a difference. I think you'd get melt at the bottom of your snowpack due to soil. I don't think it would change.
Okay.
Yeah.
So maybe you're saying one of our layers, we might not have any snow layers at some point, and that would be causing us to be sublimating from the snow, even though it says the sublimating from the soil, even though it says it's snow.
Yeah, I think maybe if you follow up, like you're looking.
Okay, yeah, we'll look into that.
Yeah. Other questions?
I have a question. Did you guys have like an initial hypothesis based on maybe which model might do better, knowing anything about the Umpqua soil or the soil at that site?
We didn't have a specific hypothesis from the beginning because the idea of the project was to try and to experience each simulation and see what the results would be, and then try to understand what's happening. So yeah, we didn't came up with an initial hypothesis.
Time for one more question. Anybody? If you have time, you should run it again with Madison data because I think you'll get way more interesting stuff. Like Oregon, the soil almost never freezes or does anything very interesting. So. All right. So who of Sarah, Drew, and Maggie would like to be the presenter?
I'll present.
All right, make Sarah the presenter.
And let me know.
Be the presenter now.
Can you see that?
Yes, excellent. All right.
Okay, are we going to get started then? Can everyone hear me?
Yes, excellent.
Perfect. Okay, so my name is Drew Stock. I'm at USU, and so is Sarah Goking. And then Maggie Kraft is at Boise State right now, and we are going to be presenting what we found on the effects of changing the canopy shortwave radiation setting in SUMA. Next, we'll just give an overall layout of what our presentation is going to be about and talk about the changes that we made to the settings. So the decision that we changed within SUMA was this Canopy SRAD decision, and there were 5 different options that you can see on there. So the default option is CLM2 stream, which we were hoping would be fairly accurate because they default to that, as well as UEB2 stream was an option, NOAA MP, and then NL scatter and Beer's law. So those were the 5 decisions. You can see on the right, that's just a graph of the shortwave radiation above the canopy. So we're going to see how it's actually affecting the shortwave radiation within the canopy, how that will affect the different settings we use in our snow mass balances, starting with the canopy interception.
So we looked at both scalar canopy ice and scalar canopy liquids. And first, we saw that over the entire simulation period, that there were barely observable differences in canopy ice. But then when we looked more closely at individual periods of about 7 to 10 days, we found that there were observable differences, mainly when there were big storms. So there was a lot of interception. On these plots, it was sometimes as high as 20 kilograms per square meter. And then also, after there was a fairly big storm, and then a period of decreasing interception, and then another storm. And that was often when we would see differences in canopy ice. So then we looked at canopy liquid and total canopy water content. I'll turn it over to Maggie for that.
So this is canopy water content. So this is on the left is a zoomed in of the different models, and this is in March. And then on the right, this is cumulative water content. And so as Sarah just said, you only really saw a change in the water content in the canopy before and after the big storms. And then just kind of trying to think about, okay, well, does this, how does this change throughout the entire season? It really didn't have much of a difference between each of the models throughout the entire season. But the UEB was the lowest and the NL scatter was the highest, but it didn't make too much of a difference.
Talking mute.
Thank you. Okay. Can you hear me? Can you guys hear me?
Yes. Yes.
Okay, thank you. Sorry, I heard a really weird feedback noise for a minute. And now okay, there. Just I hope you guys can't hear that, but it's really loud feedback. So we thought that the different canopy attenuation or the radiation attenuation methods might affect not only the interception, but also the amount of radiation getting through the canopy. And so we looked at some snowpack variables too. And the first one was Swee, so scalar Swee. And during the accumulation period, the 5 different methods were really similar, but they started diverging in late February. And by the end of the ablation period, first the max Swee was different among all of them, with the default method, the CLM2 stream, having the lowest total max Swee, and then the earliest melt. So both the max Swee and then the snow disappearance date were different. And then also I noticed that the total max Swee was pretty large compared to the amount of snow that was intercepted during some of those big storms.
Okay, so these images show scalar throughfall, which refers to the amount of snowfall that reaches the ground without touching the canopy. So we didn't expect to see very many changes between there, and that was the case. You have to zoom into really just a 4-day period, as you can see on the right-hand side, to see any differences. And in that figure, so that's showing March 1st to the 4th of 1997, and you can kind of see it in the first couple of days there's an oranger line that's lower below the red, and that is the CLM2 stream. So you're seeing slightly less of that scalar throughfall from the CLM2 stream method, probably implying that there's more interception within that method. The next slide shows the scalar snow depth. So as you can see here, the left-hand side is our total time period, and the right-hand side is showing March through May of 1997. You also saw variability in the Swee during that time period, which corresponds to differences within the scalar snow depth. And the lowest line here is the CLM2 stream, while the method that had the highest amount of scalar snow depth would be the Beer's law up there along the top. Next, we'll go into sublimation.
Can't hear you.
We expected that the method of shortwave radiation attenuation that we selected might affect sublimation, but the differences were really very tiny, and this was actually the largest difference that I saw. So here I'm zoomed into a 10-day period, and there's just a very tiny difference between the UEB2 stream and all the other methods. So that expectation wasn't met.
So related to sublimation, looking at like latent heat and then sensible heat. So again, on the top plots are cumulative throughout the entire season of latent heat and sensible heat, and then on the bottom are just zoomed in sections. Those are both in February. So for both of them, when you zoom in, there wasn't really any kind of pattern you could pick out from day-to-day variation. And looking at the entire season was just like a disaster. So, but when you look at the cumulative, there was sensible heat did have a variation between the different methods. So basically, we are gaining heat in the system, but not enough to change phase, but the sensible heat is changing. So in the sensible heat, the Beer's law and NL scatter have the highest sensible heat. Next. So then thinking about snow surface temperature, there really wasn't any big differences during the accumulation and ripening phase, but we did see differences during the melt period. And the differences occurred mostly during the lowest temperatures, and this likely affected the snow disappearance states. And then similarly with vegetation temperature, the vegetation, like the mean values and max values, they all were pretty similar. And once again, like the biggest variation occurred during the lowest temperatures rather than the highest temperatures throughout, yeah. So then thinking about, okay, well, just, comparing vegetation temperatures to air temperatures and what that means for like estimating long wave radiation. So the plot on the left is the difference between air temperature and vegetation temperature throughout the entire season. So the biggest differences between the two occur in the spring, and on the right, this just shows, the vegetation temperature is more extreme than air temperature. So you get higher highs and lower lows in the vegetation temperature. So this just kind of looking at and showing the implications for estimating like long wave radiation, and thinking about when you do estimate long wave radiation, where your temperatures are coming from and whether the shortwave radiation attenuation method will affect your outcome values and whether you're using air temperature. Next.
So just overall, we found that the default method, that CLM2 stream, which is the community land model, it had the highest canopy storage, earliest snow disappearance, and least amount of snow water equivalent. We didn't see really any big differences between the different methods on surface temperature or vegetation temperature, and we didn't have any observed data to compare this to, so we couldn't say which is the best model, but we think it really just depends on your project. I mean, if you really care about the melting period, it makes a big difference which method you choose. And you care about that amount of snow water equivalent, you might choose one method. While if you care about different characteristics, you might choose a different method, which is what we've seen on the other homeworks. Especially, we did another homework 2, that had another CLM method, and that was on the number of layers. So if you have a more, like an avalanche project, you might need more layers than if you were doing a different type of project. So whichever method you use mostly just depends on what you care about, like what your desired outputs are, or where you are located and what the climate's like in those areas. Does anyone have any questions about our presentation?
I have one. So what about Umpqua climate do you think made it uniquely not sensitive to changes in shortwave attenuation by the canopy?
I wondered if maybe it was because the temperatures that we saw were fairly close to 273, and I wondered if maybe in a colder temperature it would be more sensitive, that the system might be driven more by the long wave radiation.
So how about, did you make any plots of the incoming shortwave radiation?
It's probably pretty variable and probably a lot of cloud cover.
It wouldn't let us make plots of what the surface shortwave radiation was, like the net radiation. That wasn't an option in like the output. So we weren't able to like say, well, this is what the shortwave radiation is after we use the method. We were only able to say this is the shortwave radiation at the top of the canopy.
So you couldn't see the shortwave under the canopy after you attenuated it?
Yeah.
I'll see if I can figure that out for next year. Other
Yeah,
questions?
there were variables listed in the PySumma how-to that were giving us errors when we tried to pull them out.
I think what happened is that if you output everything calculated by the Summa model, you get these giant files. And so I think that Bart and Andrew made some judicious decisions about what we might want. And you have to actually change the output file, which I don't think we went into, if that makes sense. You can output more things than were actually being written to the output file.
Okay.
Yeah. Other questions?
This one's kind of simple, but if you go back to the snow fall through slide, I just was wondering a little bit about the units on that one. Do they measure like a volume coming down? Is that?
So that's in kilograms per meter squared second. So weight
Rate.
per length of time. Thanks for time.
It's kind of like snowfall, just like snowfall under the canopy. Any other questions? All right, Chris, Josh, and Megan, who wants to control the presentation?
I can drive.
Okay, I'll give it to Chris. And I wanted to also say everyone's done an awesome job so far. You guys are doing great. You just can't hear us clap due to all the mutings. Okay, Chris, you should be the presenter now.
Okay. I do have my webcam off. My computer says I have like low internet connection, so that's why y'all can't see me.
Okay, we can see your screen.
Right. Can you guys hear me? Cool. So I'm Josh, and me and my partners, Chris and Megan, did the project wind adjustments analysis at the Umpqua Oregon site. This is a picture that I took in the Umpqua National Forest a couple years ago. Pretty cool storm. You can go to the next slide. So the questions we wanted to answer, the first one was, how does a relatively small change in wind forcing data affect snow accumulation? The second question we wanted to answer was, does the effect of a forcing change vary between forest and open areas? And lastly, what effect does changing the wind profile beneath the canopy have on snow? So the methods, so what we actually did in our project is we changed the wind forcing data up 10% and then also down 10%. And we also changed the wind profile below the canopy from the logarithmic method to exponential. So both of these pictures right here are kind of showing generally what we did in this project. So you can go to the next one. So the first plots we have here are looking at Swee using increase and decrease wind speeds. And the one on the left is in the forest, and the one on the right is in the clearing. So in the forest, increased winds, the Swee more closely matched the observed Swee that was seen in the forest, and a decrease in wind caused an increase in Swee. So that's just kind of saying that like the wind wasn't blowing as much of the snow away. And there was a small Swee differences during the initial accumulation. So during the beginning months of the winter, there's not very much change between the different simulations. So then in the clearing graph, It's kind of the same thing where there wasn't much difference in Swee during the initial accumulation, but the decreased wind more closely matched the observed in the open area, and the decreased wind had an increase of Swee in the open area, so kind of the same thing that was seen in the forest for decreasing wind. And in the increased wind caused an earlier melt, and I think that's just kind of because there was increased like turbulent fluxes such as latent heat during that time of year, so that would cause snow to melt earlier. You can go to the next one.
Okay, so we just kind of looked at Swee on that. Now we have two plots on here. We have snow depth and the snow density. So kind of wanted to spread out. Again, we have clearing as blue, forest as orange, and that the solid lines are when that's the base, and then the perturbed wind from there. So I wanted to show again that at the beginning of the accumulation season, that's like where the model starts to diverge. To me, that was a little bit counterintuitive. I can go more into that later, but the general trends that we see are when you increase the wind, you're basically having a shallower snow because more is blowing away. And conversely, when you decrease the wind, you're getting deeper snow because less of it is blowing away. And so to really kind of hone into how that affects accumulation, I tried to split it up in terms of sort of these periods, these accumulation, this like sort of neutral area with the snow depth, and then the accumulation again, and then back to melt. And so the differences there are the mean differences of the depth between the baseline with either the decrease or the baseline and the increase. And so for that beginning period where you don't see much divergence, there's only a centimeter difference. And then when the snow is pretty stable throughout the midwinter, it's 4.5 centimeters. And then it increases, so the accumulation there does increase after the model's already kind of diverged. And then we see the biggest one during the melt season. I was pretty curious like why the model was diverging, whether it was like the timing and just that midwinter part, or it does happen right after the depth, it rapidly decreases. So we sort of attempt to answer that later. The density is a zoomed in plot. This is the plot on the right now. That's zoomed in for a period of time that we saw the biggest differences. Density basically tracked really similar the whole way. There weren't huge differences, and wind can be very well known for blowing across the surface and making it denser. So I was expecting to maybe see some larger differences, but what's interesting is when we get right into March 15th, in the clearing, in the clearing, you're looking at the blue lines, you start to see both the increased wind and the baseline wind track up and gain density, whereas the decreased one, it's not losing it, but it's just hovering the same, and they start to differ by 100 kilograms per meter cubed. I think 100 kilograms per meter cubed is kind of a lot in terms of snow density. And then you do see the squared bit there where the increased one really drops, but we know that that's because earlier on the Swee dropped down to 0, so that equation made it drop. Yeah, that's kind of explains those ones.
Okay, so I'm going to talk a little bit about what we saw when we changed the wind profile. And I started out by trying to understand a little bit better about what was going on here, like physically. And so here's my little sketch of that. So essentially at the top, you've got the wind that comes out of the forcing file that's applied at the measurement height. And then the wind profile is essentially representing like the interaction of the boundary layer caused by the ground and the canopy. And I guess what I didn't understand early on, what came to find out is that changing the wind profile only really changes the shape of that velocity profile below the canopy, so between the canopy bottom and the snow surface. And there's a whole portion of that profile from the canopy top to the canopy bottom, that changing wind profile does not change. So below the canopy, from the canopy bottom to the snow surface, the default option is the log shape. And the shapes here, these are just kind of notional, just probably not exactly what they actually are, but this log shape is what the default is. And so the option was to change to this exponential shape. And the end result of that is a reduction in ground resistance, which I translated to mean that you end up with higher wind speeds between the canopy bottom and the snow surface. And so, so looking at the plot here, the solid orange is the in the forest, blue is in the clearing. And so the solid orange is the logarithmic profile. And so the ground resistance in the forest is basically the same with the log profile, is basically the same as it is out in the clearing. But then when we change to the exponential profile, you see there's a pretty dramatic like order of magnitude reduction in that ground resistance. And it seems like that translates to increased wind speed below the canopy. And that increases the energy exchange near the surface, at the surface. So those are kind of seems like what the mechanisms are. And so if we take that in to the discussion about what happens to Swee, so there's a lot going on this plot, but we'll kind of step through it. So starting over here in the early part of the season, you can see that so what we have here is again, the orange is in the forest, the solid is the log wind profile, the dashed is the exponential wind profile, the blue is in the clearing, and this is really just on here for reference. I'm not really going to talk to it too much. And then the black is the observations. So all of these track pretty well through the early part of the season, and both are doing a pretty good job of matching the observations. And in the blue box here, overall until like kind of out in January, the log profile is doing the best job of matching the observations. And then interestingly enough, over here out at the end of the season, in the green box, the exponential profile is kind of matching best to the observations, with the exception of this. It's still kind of overestimating the melt rate. But so one interesting thing that I wanted to dive into here was in this red box here, and it's really where the simulations start to diverge really dramatically. So there's a big drop in Swee here with the exponential profile. And so if we zoom in on that, and so this is that area kind of zoomed in here. We're basically looking at this December 10th time frame where there's this significant drop in Swee. And then if we go over here on the left-hand side, these are kind of zoomed in plots of air temperature, wind speed around that same time. And so we were trying to piece together the story of what's happening. And what it looks like is this is the first significant period of above freezing temperatures. Of above freezing temperatures in that area, combined with some higher wind speeds, and both of those two combined with that exponential profile to create like a pretty significant increase in the sensible heat for the exponential profile only. You kind of see in the dash here, it's much bigger than the log profile. And so we hypothesized that both of those, kind of all those factors, go into this drop in Swee. So to look at depth, it's a little bit of a similar story, and it's to Swee. But the things that I wanted to highlight here are, so the black line, here's this sort of that big drop in depth that we saw earlier on in the Swee plot. But the interesting thing in terms of accumulation if we look at like pretty much anywhere where there's large accumulations or even the small ones, the magnitude of the accumulation with the log profile is pretty much the same as it is with the exponential profile. And so here's a good example of that. And then this large accumulation in the late season as well is the same. So that was kind of an interesting result. And then just sort of pointing out that really early on, the effect of this, the exponential profile is to completely melt out the midwinter snowpack.
So before I read you this takeaway slide, just to kind of give it more context on kind of what we got out of this project, we sort of know that wind isn't necessarily the largest driver in terms of accumulation and melt, but we found out through the research profile that the three of us were all pretty interested in spatial effects and distribution of snow. So we kind of thought this was a neat project to be able to sort of change the wind at one spot and change the wind profile at one spot, and sort of see what differences to expect, because likely in that same area, the wind is experiencing more or less, or the wind profile is kind of changing. So we thought that was kind of a unique way to do it when SUMA is really good at doing like the point stuff. This was kind of our attempt at looking spatially a little bit, or thinking about it like that. So the takeaways from this one are that with small changes in the wind speed, we get plus or minus 5 centimeters of snow depth. Generally, that's the error of, it's more than the error of like a manual measurement, less than the error of like an airborne measurement. The Swee was different by about plus or minus 22 kilograms per meter squared, and overall the biggest part of density that varied was when you increase the wind. But over accumulation, which was our original question, there's sort of little effect when you disturb the wind like that in the beginning of the season. For the wind profile, below the canopy, it has a significant effect more during the melt cycles, both the midwinter and the spring. That's where we see the largest effect. The exponential profile, changing that option, caused the lower ground resistance, which then made a greater like surface energy exchange with like how we kind of looked at the sensible then we looked at the sensible heat from the canopy, and then the warmer temperatures and winds cause more melt. The profile effects then on accumulation were also minimal, is what we concluded.
Thank you. Any questions? I want to make a statement. Megan I think Joshua was saying the wind can blow the snow away and the wind could make it denser. This can happen in the real world. It's not possible in SUMA. So SUMA does not do wind redistribution, and SUMA does not have a wind-based density compaction. So basically everything you were seeing everywhere was actually related to the turbulent heat flux.
Okay.
So, I mean, there were fair assumptions for real snow, right? But it's just not possible in SUMA. It doesn't have parameters to do that. Mm-hmm.
Sure, and I actually did question that. I didn't dive further in to really answer that, but I think that's what led towards let's look at sensible heat and see where those changes are.
Yeah, so the sensible heat was happening in the open and under the canopy. And so what you end up seeing is that for a really warm place like the Pacific West, sensible heat flux starts mattering a lot.
So Jessica, you're saying that the wind the only effect the wind has is to drive the turbulent flux in the model, like that's it?
Yeah.
Okay.
Yeah, the in SUMA as currently configured, the wind does not blow or redistribute snow. So if you had Glenn Liston's model, which I showed you, I think last week, it blows the snow around, but SUMA does not blow the snow around. So it's both the latent and the sensible heat flux. That's what the wind is doing. Other questions?
I have a question about like, which you guys might not know the answer of, but how does it determine what the like trunk height or whatever of the model of the forest is for the log versus exponential profile? Like just looking at like that picture that you guys have up in your questions, I don't see any, like those trees, you don't really see the trunk. And so like, if like, what is that height? I guess like, what is that height?
So my understanding is that you define this height here, the height from the ground to the bottom of the canopy. And then there's other heights that are defined as well. But in terms of what we're concerned with here, you can define that number. And so as your snow grows, like the region where this wind profile makes any difference at all gets smaller and smaller, and eventually, like if the snow height is above the canopy bottom, I would imagine this would have no effect. Here, like, you know, this height is 2 meters. I went in and checked it, and like the snow depths that we're showing under the forest are, you know, I think maxed out at like 1 meter, so or not even quite. So there's still about 1 meter of height where this is having an effect. But I think you can change that to whatever you want it to be.
Yeah, it's in your site profile. You set it up and you tell it what kind of vegetation you have, how tall it is, and then you say where the trunk height is. I think something to remember with all of these, I mean, you guys did not have time to dive into it, but every single one of these choices also has a whole lot of parameters associated with it. And often changing those parameters makes even more difference than changing the choice. Similar for the short-wave attenuation, each one of those were a different functional form, but there were parameters that if you'd also tweaked, you might have changed short-wave radiation quite a bit more. So you can, in addition to choosing log and exponential, you can also change the shape of it, like how sharp of a log profile is it, which will also affect things. Just be aware of for the future if you're diving into these. All right. For Locksmith, Brent, and Connor, who wants to run the PowerPoint?
I can run the PowerPoint.
Okay. I'm giving it to Locksmith?
Yep.
All right. Okay. You should be the presenter now. There we go. I see it now.
You all can see the PowerPoint?
Can you like go to presentation mode, full screen? Yeah, that's good.
All right, ready? So I'm Connor, and I'm with Brent and Lashley, and we're presenting effects of the albedo decay rate on snow modeling. And so on our first slide, we actually look at the next slide. we see the equations for albedo. So the first one is just the general one for how albedo is used, at using snow cover fraction and the albedo of the snow and the albedo of the soil. And so this decay is specifically for the snow albedo. And there's two options in the SUMA model. There's the constant albedo decay and the variable albedo decay. And so that second equation there is the equation for the constant albedo decay. And it simply goes down with time at a constant rate. And the second one, the variable, it changes based on location. And those three R's that affect albedo, it's the snow grain growth with vapor diffusivity, and it's also the grain growth at about freezing point. And then it's also R3 is the effect of soot and dirt on the snow. So it has lots of other factors to affect how the albedo is going down. But the general idea is that albedo goes down after it first falls down, and albedo continues to decrease with time. And with that constant one, the number 3600 is one that you can change in the model. And so we actually did play around with that number as well, doubling it and putting it in half to see the effect of changing that parameter. So the next slide, we see the Swee with these different decay rates of albedo. And so this is for the 2 years, and you'll see first off that for most of the time, there's no difference at all. But all four of them are essentially giving you the same thing. But where you do see a difference is in the melt period. And the variable decay and the constant decay with the 360 rate, which was the default, are fairly similar, but the other two have more variation. And so if you zoom in, the next slide zooms in onto the melt period for the first year. And we can see that the lower decay rate, which remember it's in the denominator, so it means that a lower decay rate, the lower number means it decays faster. And so when albedo decays faster, that means it can absorb more heat. And so naturally it's melting faster. And for the larger number, that means it's going to decay much more slowly. And so it melts slower. And so you see that with the red and the green lines there, whereas the 360 and the variable are very similar, but the other two have vast differences. And the next slide shows the second year. And this one you see a similar pattern, but it's not quite as much difference, because in that first year, there was a period after melt had started that there was some accumulation seen in most of them. And during the accumulation, during the melt, there was a lot more variation, whereas in the second year, it was pretty much just straight up melt. And so the 360 and the variable decay albedo have essentially no difference, but the other two still do have the differences naturally, because albedo does affect how much energy it's absorbing from radiation. And then going on to the next slide, Laxi is going to talk about density.
Oh, thanks, Connor. So as Connor was talking, we looked into the different decay rates, and for the constant decay, we looked into how the same constant decay, if we reduce it to 50% and also increase the decay rate by 50%, what happens to the snow density. Along with that, we also looked into the variable decay. So what we found with the density was albedo has an inverse relationship with the snow density. Like for the constant decay, if the albedo decay is going up, the snow density is decreasing. The reason is that if the albedo is decaying faster, the snow is melting faster and producing less snow density. Whereas if the albedo decay is if the albedo is not decaying faster, like you can see the green line, so the snow is not melting very fast, and which is resulting in higher density. And this trend was similar throughout the simulation period. For the 2 years, the lower the albedo, the higher the snow density. And when we compare between the variable decay and the constant decay, there is no much difference in any period. Like it could be either the active melting period or it could be like a non-melting period. So we kind of looked into one particular period, like how albedo decay has effect on snow density, and this is for the 2 months, January to February of 2011. So the trend followed by the snow density was same for all the different decay rates, but the magnitudes are different here. Like the green line with the smaller decay rate, it produced higher density, whereas the decay rate with the red line with higher decay rate produced lesser snow density. And this is like, and the reason is like directly related with the snow melting. Like the higher the decay rate, faster the snow melting, and which would result in lower snow densities. Whereas there is the constant decay and the variable decay, they kind of coincided. There is no much difference in the snow density for the first 2 months, like at least January and February. And this is for the next year, for the 2012. The reasons are the same, like the trends followed are same, but they differ in magnitude, and it is kind of direct proportional to how snow is decaying. So we also looked into the snow surface temperature. This is for like the melt period, like for 20 days of May, like May 1st to May 20. So here, like if the snow is melting faster, that means that if it has a higher decay rate, this it is causing the recrystallization of the snow, and like the solar radiation or the incident radiation can easily penetrate into the snow, and which can increase the temperature of the snow, which you can see here for the red line, which is like a higher decay rate, whereas the snow with lower decay rate, the temperature change is not as variable as with the higher decay rates. And again, there is no much difference between constant and variable decays. And this is the snow temperature for 2011, and this is during the month of June, like for 5 days of June. So here, the green line shows the lower decay rates. So since it is not decaying faster, and the absorbance of the solar radiation is not high, and the temperature is kind of fluctuating, whereas with the one with highest albedo, like the decay is faster and it is absorbing more solar radiation, producing more fluctuations. And as I said before, the variable and constant did not show much difference in the snow surface temperature. So Brent will talk about the sublimation, and I'll continue the presentation.
Thanks, Laxmi. So I'll talk about snow sublimation. So the change from frozen water, snow to back to the air. So you can see on the graph, either it's going to be positive or negative depending if it's going to the air or to the snow. And you get a better idea from this graph looking at the cumulative graph between the four methods. So go to the next slide. So we can see the more variance across the four different methods with the cumulative graph. Like Connor and Laxmi were saying, the preset method, the 360,000 for constant decay, was very similar to the variable decay method. This was similar results to that paper we read at the beginning of the class, or the Clark et al. 2015 paper. They did a study on Reynolds Mountain and Senator Beck sites, and they found something similar, that it was looked very similar, indistinguishable between two methods. However, we do see, of course, that the upper and lower decay rates vary quite a bit, just depending on how much snow is available for sublimation. Next slide. Some conclusions that we learned from the study. The variable albedo and constant albedo decay of 360,000 from that equation we showed at the beginning. Rates did not produce significant difference among the Swee, snow density, and sublimation, and that most variation between the albedo decay was observed during the melt period in the summer months. And I think that's it. Thanks, guys.
Thank you. Any questions? I always have questions. Can you go back to the snow surface temperature slide? This one. At what temperature does snow melt?
This is the one showing where the different ones started melting. So when it goes above that straight red line, its snow is completely melted.
Snow is gone, right?
Yeah.
Yep. Snow is all gone. So so which one was absorbing the most solar radiation? Which one had the lowest albedo, most solar radiation?
The 180K.
Yeah.
The green one, right?
Yeah, the green one.
Okay. I think at some points during the discussion I was getting really confused which line was which. I think just one I did because albedo decay rates are kind of confusing, right? Faster rates actually mean lowered albedo. So I think if you're talking about albedo again, like just having a kind of slowing down and showing people like what's which and what does it mean, and then I think also for an audience, anytime you're showing a snow surface temperature plot with it disappearing, like just make sure your audience knows what's going on because it's easy to confuse lots of people. But very clear results. Other questions?
What's the picture of on your question slide?
No one's telling?
No, this is my experimental slide. Actually, I conduct the like winter experiment on these plots. Basically, this is cornfield. I look into the soil nutrient migration during winters, and also like with the snow cover, how the heat moves within the soil profile, and how it affects the nutrient migration. Yeah, this is in Madison, Wisconsin.
Very cool. All right, so I believe we got 2 more groups, so we're gonna have to move quickly here. Who of Eduardo, Peter, and Allison would like to drive?
I think I'm going to present or be the presenter.
Hand over to Peter right now. Okay, you should have presenter status now.
Awesome.
All right, I see your screen. Great.
Awesome. So my name is Peter Youngblood, and I did this final project with Eduardo Gonzalez and Allison Vincent. Sorry. We're looking at a climate change scenario and what that would look like for a snowpack. And in addition to that, we also change a couple other parameters and see what the output is. So we're taking a look at the UMQUA site for the water year 1997, or in other words, what we were doing in our homework. For the temperature manipulations, we changed it to three different scenarios, one with 1.5 degrees Celsius, 2.0, and a 2.5 degrees Celsius. We also took a look at the wind speed variable and the wind profile, as well as the snow incept to change it between sticky or light snow. So to jump right into the climate change scenario, if we're looking at increasing temperatures, if you were just to change or increase the temperature by 1.5 degrees Celsius at the UMQUA site, it has a very drastic change on the peak Swee, or the overall snow that you get throughout the wintertime. You can actually see it's a 47% decrease in peak Swee at this site. And a large part of that comes in December, when you get this large accumulation and then pretty much all the snow melts away. Whereas in comparison, if you look at the current model, then it models that snow to stay around for quite a while. So we took a look at the air temperatures for the month of December. And one thing that you might notice if you look at the plot to the left, the blue solid line is the observed air temperature, and it sits just below freezing. So even a small increase, which is as small as 1.5 degrees Celsius up to 2.5, that brings the average temperature to above freezing for that month. And you can see that even more so in the histograms to the right. So those histograms plot just the observed air temperature for December. But you could go through and look at the observed air temperatures for the entire winter and see that it forms a pretty normal distribution, which is centered right at 0 degrees. And just that small change in temperature pushes it so that a majority of the time it's actually warmer than freezing. So that has a huge impact on the amount of Swee that is at the site. And you can see that even further if you increase it by 2 degrees Celsius. See that it's actually a 58% decrease in peak Swee. And even more so if you look at the 2.5 degrees Celsius increase, and that's 72% decrease in peak Swee. And so this really comes to show how important or how critical climate change could be for these snowpacks in a warmer climate where it's usually around freezing for most of the winter time. And with that, I'll pass you on to Eduardo.
Can you guys hear me? Good. Okay, so besides doing just a climate change scenario by modifying temperature, we also decided to change wind speed and examine the effects on the simulation. To do this, we created two plots, one of them showing the snow water equivalent at the forest with different wind speed, and the second one the clearing or the grassland. We did not use the same wind speed for both simulation, and the reason for that is because for SUMA, the forcing variables are specified above the tree canopy. So for most of the forcing variables, actually, it doesn't make much difference. However, in this case, for the wind speed, it does. So, and this is because, well, we have a much lower wind speed near the ground in the clearing than above the tree canopy. So this is a snow water equivalent plot as the grassland, and the solid blue line represents the observed data, the green line, the default simulation. That is the simulation that was done in homework 1. The red line represents an increase in wind speed. It's actually, a decrease. A decrease in wind speed. Yeah, the red one. So it's actually 0.9 times the wind speed that was used for default simulation. And lastly, the purple one is an increase of 0.105 times the default wind speed. So if you notice, the simulation is really sensitive to wind speed changes, and the best simulation we have is the one with the lower speed. It's not actually too good when it comes to modeling the melting season, and the reason for that is because a higher wind is likely to melt the snow that is close to freezing. Can you go to the next slide?
So yeah, on this one we have the snow water equivalent again. Blue line, observed data, green line, default simulation. And if you remember from homework 1, the wind speed at the forest is around 1.6 times the wind speed at the grassland. So the red line here is 2 times the wind speed that was used for the default simulation. And lastly, the purple one is 2.5 times the default speed. And we see a complete different pattern as the one we saw in the grassland. Here, the higher the wind speed, the better the simulation. And it's actually better when it comes to modeling the melting season with a higher accuracy. And based on the graph, yeah, we know that the snow lasted longer in the open, meaning that we had a warmer winter, and warmer snow is actually more cohesive and less subject to wind. Next slide. So we decided to also change the wind profile, the decision from log below canopy to exponential, and plotted the snow water equivalent for both the forest and the clearing in the same figure. So here we use, and we actually use the default wind speed for both the forest and the clearing. The blue line is the grassland and the yellow line is the forest. For the forest simulation, even though the exponential decision underestimates, the observed data is more accurate than the log below canopy simulation. And as Chris mentioned before, the grassland simulation actually doesn't work when it comes to when you try to use the exponential profile. So, and we actually noticed that if we use the exponential decision, the wind speed will increase faster, and because we have if it is too high, then we would have like enough snow accumulation. So next slide. Yeah, that's it.
Okay, so for the last variable that we looked at, we decided to look at what happens if we change the snow to the snow intercept value or decision, sorry, to be either sticky snow or light snow. So light snow is the default value that we used in our homework. And so this is, I guess I'll back up for a second. So we decided to do this for a couple of reasons in our climate change scenario, because as we talked about, with warming temperatures, snow generally goes from light to sticky, and that will affect how much of it sticks to the canopy versus how much falls through to the ground. And then also, it's not represented in our model as we talked about, but in theory, wind and stickiness of snow would also have a relationship. Wind or light snow is more likely to be blown around by the wind than sticky snow. So this first plot here is the sticky versus light snow for the forest. And so as you can see, we have significantly higher Swee with our light snow than we do with our sticky snow, so because Swee is just being measured on the ground, and then the observations are just there for reference. Go ahead and go to the next slide. So then does Swee change in the clearing? It shouldn't, obviously, because this decision is all about the trees. So this is just kind of a reference. We just wanted to make sure that the model indeed was not changing Swee in the clearing, and we can see it the change. There's a little bit of variation here and there, but it's for the most part pretty much the same. And this will be important for one of the graphs that we look at later on. Let's go ahead and go to the next slide. So then the next thing that we looked at was differences in through-fall snow and canopy unloading. And so the through-fall snow is over on the left, and the orange is for the light snow, and the blue is for the sticky snow. And as we can see, the light snow, there's a lot more through-fall, or significantly more through-fall than the sticky snow. And it's interesting to note, so this was mentioned before, but through fall is measured as the amount of snow that hits the ground without ever touching the canopy, which I thought was kind of interesting when I first looked at it. I didn't realize that it was not looking at snow that hit the trees. So my hypothesis with this is that when you have sticky snow building up on your canopy, apparently when you get to certain points, you have enough of it building and more mass that you are somewhat closing in the canopy, I suppose. These values are obviously, there's a very small difference in between them, but there's enough that it's measurable when you have snow accumulating on the canopy versus not. And so then the plot on the right shows our canopy unloading, which is pretty much an inverse of the through fall, which we would expect. So that's just showing that with our light snow, we have a lot less snow being unloaded from the trees because it's not getting hung up there in the first place. And with sticky snow, we have a lot larger values of canopy unloading when that does happen. Okay, go ahead and go to the next slide. And then lastly, we just wanted to look at the change in the timing of the melt in the clearing versus the trees with the sticky snow. So we talked about this in lecture when we talked about what the relationship between trees and snow. So as we can see here, we have the two forest Swee plots, and then we have just the one clearing as we established that both of them are the same. So we just picked the light, the Swee curve for the light snow clearing. And so in addition to having more snow on the ground in the forest, so with light snow, the snow sticks around longer, obviously, because more snow takes longer to melt. And it's interesting to note that while the sticky snow, in this simulation, we don't have the forest melting before the clearing that we would expect to see, but we do, that timing has shortened a lot. And so if we had additional variables included in this simulation, such as temperature and other parameters that we might see change due to climate change, it might be very easy to see that switch and to have the forest melting out before the clearing. Next slide. So to conclude, for our climate change scenarios, we found that a relatively small increase in temperature can lead to significantly less snow. Wind speeds were faster, increased more quickly with the exponential decisions, and then hence the snow accumulation was less. And the stickiness of the snow alters its interaction with the trees, and which impacts the amount of snow on the ground and ultimately its melt timing. So to sum all of this up, it appears that the snow we know today may be very different in the future. And with that, we'll take any questions.
I'll take one quick question. And I'm hoping nobody in the last group has to be anywhere right after. We should be able, if you guys can stay for 10 more minutes. Apologize for running late. I want everyone to be able to get through if they can. Any quick questions here? Okay, last group, Katie's in the last group. Does she have to run away? You're okay? Who wants to control, the screen? Anybody? Not hearing anything. Are you chatting? Jessica, Katie, and Victoria.
Yeah.
Hello?
I'll turn it off your mute. Hey, can you hear me? This is Katie.
Katie, you want to be the presenter? Yes.
Can you actually make Victoria the presenter? We're just going to use my
Victoria
audio.
Be the presenter now.
Okay. And great.
Can everyone see that?
Can everyone see Victoria's screen? Yep. Okay, great. And then it's in, somehow it's not hold on one second. We're still,
not showing?
it's not showing presenter mode. We're like showing the presentation.
It actually looks perfect.
Oh, there it is. Okay, that's weird.
Maybe it was just a quick lag.
The prior one was better.
Oxymoron.
Okay, great.
Okay. Hi, my name is Jessica. Can everybody can hear me? Yes, thank you. We're going to do. We're looking to look for the impact of the drain and rate parameters and the layer and scheme for modeling the snowpack. So the next slide, please. Next slide. Okay. Our research. Okay. Our research question are the following: is the how do capillarity rotation and hydraulic conductivity and exponent for melting flow change the rate of which water travels through the snowpack? So the next question is we try to answer is, does changing the layering scheme revealing further difference in varying draining rate parameters? So we was curious in changing the model parameters for draining rates and the model structure layer like we do for homework 2. So the next slide, please. And this is the site we are doing our study. It's the Sierra Nevada, California. In the next slide.
Maybe I'll just turn back really quick and go forward. Interesting. Maybe I can just do this and then click present once more.
Is slide 5 work? Is it just slide 4?
Is it just slide 4?
That's so odd.
Will it work if I just show it small? Looks like the graph is also not showing up. Is it showing up on the screen? Sorry for the technical difficulties, everyone.
Yeah. I'm wondering, end of the day. I'm wondering if you want the PowerPoint. Probably should.
Okay, we'll just do this really quick. Let's see. While this is downloading, I have a great riddle. 2 penguins are in the middle of the desert, and they're both in a canoe in the middle of the desert, and one says to the other one, "Hey, where's your paddle?" And the other one says, "Sure does." Okay, well, you can think about that on your free time and email us with your responses. Okay, so going into to look at the things that we have modified in the model, we're interested in looking at drainage rate model parameters. So in order to do that, we have to look at the parameters that are related. So first, what is drainage rate? The definition of drainage rate is the rate of water it drains through to the bottom of the snowpack. So there's several variables that affect this rate. F capil is the capillary retention as a fraction of the total pore volume, and is how much liquid water you have as a fraction of how much liquid water can be held in the snowpack. K-snow is the hydraulic conductivity, and this is the rate of the water that flows through snow, aka the hydraulic conductivity of snow. And lastly, the exponent for melting flow. Previous research has found that the variables before in this equation are related to each other through this exponent c. So it's sort of this relating term that relates capillary retention and hydraulic conductivity. And above, a little bit of math to show just how they're related here. And I'm just going to go into some of the, so looking at those different parameters and changes in those parameters, we're also interested in, well, how does, if you change and kind of turn these knobs, how would that affect different snow model layer schemes? So here's just some simple diagrams or simplified diagrams to show some of the models that everyone's familiar with from homework 2. And for this, since we're looking at drainage rate, we wanted to just bring back this figure from class, looking at the 3 main phases of snowpack. 1, snow accumulation, 2, midwinter energy balance, and 3, melt. And so we wanted to concentrate just looking mostly at March and July for our analyses, since this is where we'd expect the melt to be occurring.
Great. So we've presented to you all how we are interested in both the drainage rate and then how these drainage rate parameters may also affect the model while also modeling the snow layering schemes. So we using homework 2C, which some of you all may have taken a look at. They presented 3 ways to change the drainage rate parameters. It was reducing capillary retention, doubling hydraulic conductivity, and also decreasing the exponent of the meltwater flow. And these are the 3 areas that Victoria just defined earlier in the slides using those equations. So we ran all these 5 different scenarios. The first one was kind of our control. So it was just the default of the normal like SUMA default inputs. And then scenario 5 was we changed the capillary retention, hydraulic conductivity, and the exponent of the meltwater flow. And we were sort of curious, Jessica has mentioned, how bad models can still make right results. So we were just curious if any of these interactions would somehow lead to any better adjustments. So seeing how, just taking a closer look at scenario 1, which is kind of our control, again, it's is the default setup for all the drainage rate parameters, and we ran it for all 4 layering schemes that we used in homework 2. So the 5 layering CLM, Jordan, 2 layer with a thin top and 2 layer with a thick top. I'm going to run through these pretty quickly since I know we're running tight on time, but scenario 2 looked at reducing that capillary retention, and based off homework 2C, it suggested reducing the capillary retention by a factor of 3. And we also included our hypothesis for how these might affect some of our models. And this one is if we decrease the capillary retention, so the ability of the snow capillaries to retain liquid water, it would increase the rate at which water travels through. Scenario 3, again, this is taken from homework 2C. It suggested doubling the hydraulic conductivity of snow, and we predicted that if we increase hydraulic conductivity, then it would increase the rate water travels through. And again, just like scenarios 1 and 2, we did this for all 4 layers. Scenario 4 was decreasing the exponent of meltwater flow, and if we decrease that, then it could decrease the rate at which water travels through. And then in 5, you see that we put it all together of scenarios 2 through 3, and we predicted that it would increase, again, the rate at which snow travels through.
Okay, this is our first results and how we are comparing how modeling the snow water equivalent across the 4 scenarios. As we can see how the drain rate parameters affect the snow, the timing, and maybe it's also affecting the magnitude. And we was trying to look what is the difference between these scenarios and for each modeling we was doing. So we was more interested in the 2011 snow melt phase for March and July, and we can see that reducing the capillarity and rotation and decreasing the exponent of the meltwater flow show more difference from the default scenario. And in the next slide, we have this zoom in and to look better to this part of the snow melt for edge modeling, and the snow water equivalent for various draining rate parameters, and doubling the hydraulic conductivity looks similar to the default scenario, but have the snow melt timing about the kind of the same time. So for scenario 2 and 3, they sorting the snow melt timing for all the layer scheme. Yeah, we was kind of surprised for the double hydraulic conductivity, the scenario 3, because we was expecting more difference between the snow water equivalents with the scenario, default scenario. In the next slide.
So looking a little bit more at scenario 5 was of interest because it combines all of the parameter adjustments that we were making. In comparison to scenario 1, which are along the top row, and scenario 5 along the bottom row, you can see that all of the models have an earlier snow melt, and that all models are affected by changing the parameters. The Swee values for CLM and Jordan, shown in blue and yellow, are lower by about 100 kilograms per meter squared in Swee for scenario 5. And on the right-hand side, we can see, looking at the snowmelt season, that each of the models kind of separate a little bit more clearly and have a lower Swee values in most general. And we did the same experiment for snow density. So comparing the outputs from various drainage rate parameters, we see that the initial density of snowpack varies, decreasing the exponent of meltwater flow, which is figure number 4 here, decreases the initial density of the snowpack during accumulation, and the density of lower earlier on, because of the snow can push more water through its system, so less accumulates. And then taking a closer look at the changes in density during snowmelt from April to July 2011, we see no uptick right at the end, sort of in the later season. You can see my mouse. If you can see my mouse, sorry, wrong graph. So when you decrease the exponent of the meltwater flow, you see a little bit of uptick at the end where the model parameters are showing some sort of change.
So finally, the last output we were interested in was the depth soil temperature. And it looks like we have, so we did this for, we ran this for all the scenarios, and we are curious if we would see like the soil temperature changing based off the drainage rate parameters. And interestingly enough, we thought that by reducing the capillary retention or doubling conductivity, increasing the exponent of meltwater flow would somehow change the temperature of the soil by increasing like the water that would move through the soil, potentially, especially if that would be warming up the soil after a winter. And we found that it did not appear to have a large effect on these temperature depth plots. But then we did just a closer analysis, and looking at the next slide, we were curious by just comparing the two layer models, the thin and the thick. And it was interesting to consider these adjustments to just the capillary retention as well as the exponent of the meltwater flow. And when you just look at the snow accumulation for 2011, we can see that increasing capillary retention introduces more variation in the temperature of the snowpack, and the 2-layer thin model seems to be more sensitive to these parameter changes. So finally, I know it's the end of the day, so whoever is still left, I'm going to quickly draw us to a close by saying some conclusions. The overarching conclusion is that the layering scheme does matter when you're doing these drainage rate parameter adjustments, especially when looking at the Swee values. You saw that with the more layers, the Swee values changed, especially for when you reduce the capillary retention, and also when you reduce the melt water exponent. So doing models with for these drainage rate parameters with more layers, they're more sensitive to these changes. We also saw some changes in snow density when depending on which drainage rate parameter you used. And with the SUMA doesn't seem to be as sensitive to the hydraulic conductivity changes in any of our results. It was mostly the capillary retention and the meltwater exponent that seemed to manifest certain changes in the model. So future work, we would love to explore this in different locations and also enhance the resolution for the soil temperatures, especially when looking at those temperature plots. Since we didn't see any changes, we would want to ask further questions to see if it was just because our resolution wasn't high enough. And that's it. We have lots of extra slides, but we will save your eyes for that for a later day.
Thank you so much. I think in the interest of time, I think we should just all clap for ourselves. You guys all did a great job. So you do have a few more things to do before you sign off for the class. Remember to fill out your evaluations for everybody you just saw that show up in the form of quizzes. And remember to give me feedback in the just final reflection. And I will work on getting all your homework graded and back to you within a week. But if anything else comes up, feel free to contact me via email at any time. Thank you all for participating in the class and for all these great presentations. Thank you.
Thank you.
That was a great class.
Thank you.
Thank you very much.
Thanks, Jessica.
Thanks.
Thank you, Jessica.
Bye. Thank you.